Hello, welcome everyone to the webinar today. This is the first webinar of our Research Spotlight series, and it is quite different to anything that we have done so far. We'll be chatting with 4 researchers about what it was like for them to learn to use supercomputing for their research. And our chat today is meant to be pretty casual and open. So I strongly encourage you to get comfortable, grab a cup of tea, ask questions, and just enjoy the session. But before we get into the discussion, I have a few housekeeping items to cover. If you're not asking a question in the session or speaking, we just ask that you keep your audio on mute to reduce the background noise. But if at any point you do have a question, you can pop it into the Zoom chat so that we can keep track of it and make sure everyone gets a chance to speak. Or else just signal to us that you have something that you want to say, whether it's raising your hand like this or even typing hand in the chat, just kind of carpentry style. Let me see if I can give you an example. Let's see, like so. Oops, that's not how you spell hand. And just to let us know if you have a question. We really want to hear from you guys today. And I have Jenna on the call, who's our comms manager, and she's going to be making sure that the questions are answered. And lastly, the webinar recording will be available to all of you guys. It'll be posted on the NeSI YouTube channel. And everyone that has registered for the webinar will be sent an email when that's posted. And I do encourage you all to keep your video on in the session if you're willing to have it on, just so it feels more like a group discussion. If you're not comfortable with that, that's also okay. And of course, if you don't want to appear in the recording, you might want to keep that video off. But with that out the way, that's the housekeeping stuff. I'll now introduce our awesome panelists. So we have here today Dr. Manpreet Dhami, who is a researcher and capability leader at Manaaki Whenua, Landcare Research. We also have Dr. Joe Lane, who is a computational chemist at the University of Waikato, Dr. Inga Smith, who is a physicist and senior lecturer at the University of Otago, and Andrew Pauling, PhD in atmospheric sciences at the University of Washington in Seattle. Thank you very much to our panelists for being here. Let's just dive into it. Well, we're going to start with a little bit of a warm-up question, just to get to know our panelists a little bit better and how they got started in HPC. So the question is, how did you get started with high-performance computing? And we'll start with Manpreet, because she's the first one up on our screen.
Kia ora koutou. Thanks, Megan, first for organizing this panel. I think it's a great way to get some new people who are interested into the user group. So how I started, it wasn't actually until my postdoc, which I was doing at Stanford University, that I first actually tried to use an HPC. The name of the HPC was Sherlock, which I thought at the time was pretty cool. And luckily for me at the time, a colleague was also learning, so we could join forces and go through the hurdles of learning HPC together, so it wasn't all alone.
Thank you for that. Joe, how did you get started with HPC?
Yeah, kia ora e homa. So I was down at the University of Otago, so I was a Bachelor of Science honours student, and started on some very old school SGI O2 machines, which were sort of like oversized toasters. They are a really unusual shape, but look quite kind of cool. And then sort of a year or so later, got the privilege of kind of helping to build a cluster between physics and chemistry at Otago, which was good fun. And as yeah, it was a good part of learning about making platforms accessible and making it easy for people to get on and use. And that was really a strong mandate that was given to me by my supervisor at the time, was to make things simple so that people would use them.
Nice, interesting. And Inga, how did you get started on HPC?
Yeah, so it's kind of a funny story, really. So I had kind of heard of NeSI, but kind of hadn't. And then I was at the New Zealand Institute of Physics conference in Nelson in September 2013. And I was chatting to someone, and we put our teacups down on this table. And it turned out that was the table NeSI was paying for to advertise NeSI. So they very politely sort of said to us, please, can you remove your cups because we're paying for this table? And would you like to hear about NeSI? So we had this very interesting conversation about NeSI and what it could do and what the capabilities were. And then that was kind of in the back of my mind, and I thought that's very interesting, but it's not really what I need because I do observational sea ice and I collect measurements, but I don't need to process data or do process modelling on that scale. But I'd already been collaborating with Cecilia Bitts, and she is based at the University of Washington. She's now Andrew's PhD supervisor, but she was coming out to New Zealand on a Fulbright fellowship at the end of that year. So she came out in October, went to Antarctica with us. And so she also was visiting around the country. And I think it was when she was up at the University of Auckland, she started talking to the NeSI people up there and realized that Otago could get access to PAN at no cost. It was very easy. And so she came back, and I had discussions with Blair Blakey down here as well, and Cecilia, and she offered to port code to PAN for us to see how it went. So she ported this model that's CESM, the Community Earth System model. And then Andrew had done a summer scholarship with me and colleagues previously, but he came on that year to work with Cecilia and myself and just trying to run CESM on PAN and seeing how it went, and it all went from there. So yeah, so it really just expanded the direction of my research from what was originally very observational sea ice based process modelling to something where we're now really trying to improve climate models, which is really has been a long-term aim of observations, but now we've got those good connections and capability to do it.
Awesome, really cool. I love the teacup story. That's a nice touch. And Andrew, how did you get started with high performance computing?
So I think Inga pretty much covered it because I was involved in that first project. But yeah, I started working with Inga and Cecilia in that first summer internship, and I first ran the model on the cluster here at the University of Washington remotely from Dunedin. And then we got access to PAN and were able to run sort of a larger version of the model on that. And it was kind of a whirlwind few months for me going from learning how to sort of use the command line to running a fully coupled climate model. So it was an exciting time, but now it's sort of changed the whole direction of my career, I guess, and it's got me here. So I'm now running models on the Cheyenne supercomputer which is run by the National Center of Atmospheric Research here.
Very cool. Yeah, so the ways that you each got kind of into it is quite different, but it seems like that you got into high performance computing because it was meeting a certain need and it allowed you to achieve something that you weren't able to before. Does that sound kind of correct? Cool. Very cool. All right, so we're going to dive into something a little bit different now that we know some of the background of how you got first started with HPC. I'm curious, and I did do a little prep work with our panelists and have some ideas of some interesting ways we could go. But I do invite everyone, really, if you have questions or follow-ups for our panelists, even if you are a panelist, please make sure you write it in the chat so that you guys can kind of direct our conversation here. It's supposed to be pretty casual and laid back. But I'm interested to hear about the difficulties you had when you first got started with high performance computing, some of those initial hurdles that you had to overcome to be able to even use the tool. And so let's just go with, maybe I'll start with Manpreet again. What was that kind of initial time like, and what were those initial hurdles that you had to overcome? I think you're muted, sorry.
So coming from purely a biology background, I had zero experience in anything like scripting or that kind of work. I'd done a little bit during my PhD, but writing a Slurm script, for example, was one of the hurdles. And again, it came down to just asking around, talking to people, and once you get a feel for what it means, it makes a lot of sense.
Did the other panelists, and you can signal with your hands, like know what a Slurm script or scheduling was before you got into HPC?
No, not at all. I mean, so I guess my first introduction was, it's a Linux command line, but you're on a computer, one of those old school toasters that I chucked in the chat before. But yeah, then when you transition to the computer's not connect, it's not just there. There's not the keyboard, and you start feeling a little bit worried that a network connection might drop and you'll lose information, or you kind of can't control something that you can't touch. I think that's a bit of a transition in the HPC space. But yeah, for me, I guess I had no command line experience. So learning, how to interact with a computer that wasn't using a GUI was a bit of a struggle and a challenge. And I think that's still probably the big learning curve that most people find most difficult, even whatever it is, 15, 20 years later.
Yeah, I would consider myself very much a novice to HPC, even working for NeSI. I am not an HPC user, and I imagine that would be me. I think I would be really worried I would mess something up. Did anyone else have this thought too, whenever you're getting started, that like somehow you're on this other computer, that you can do something catastrophically wrong? And if you had that thought, how did you get over that? Any thoughts on that, Andrew? Yeah.
One example where it kind of so I got rid of my fear a little bit is one early on. We were in Inga's office with Cecilia learning to compile the climate model on the HPC, and we're accidentally on the wrong node. So we weren't on the node that you were supposed to do heavy computation on, and we started compiling, and within about 30 seconds got a phone call from NeSI saying that we were using too many resources and could we please use the build node instead. So they were super nice about it, and it kind of, allayed some of my fear about messing things up.
That's so funny. Yeah. I'll just add that, yes, people are monitoring things. So if something's going really wrong, don't worry. We'll probably notice, and we'll just politely ask that, hey, what's going on? So don't fret. Inga, yeah.
That was going to be exactly my example as well, Andrew, and it was just that introduction to the politeness of NeSI as well. It was like, it was not like, what are you doing? It was like, by any chance, do you happen to be currently on the build node? Or the login node rather than the build node. Yeah, it was extremely polite, and I think that's just been consistently all the way through. Like NeSI have been really helpful. No question is too dumb. It's just a really pleasant way to kind of learn this stuff. And yeah, I mean, shows how old I am, but my PhD experience was we had a room of computers that you could use. No one had a computer at their desk, and they were alphas. So there was this, it was kind of remote, and everything was Linux and command line. And there was this idea of nicing your jobs, but it was still this completely different scale for me going to HPC. But it was also, I think, the most pleasant experience I've had with computing as well, that just everyone was really helpful and really willing to just ease you through everything. So, yeah.
Oh, thanks for, go ahead.
Yeah, sorry. I think it's a common worry that people have when they jump on an HPC platform, that they're going to break something or do something they're not meant to. But I guess what I'd encourage people is that, a lot of work goes into designing systems so that lots of people can share the same resource. So more or less, and not that people should take this as a challenge, but more or less, if you can break something, it's probably not your fault, but it's the system design not being tolerant of that's going to be the issue. Yeah, as I said, don't take that as a challenge and deliberately try and do it. But I know a lot of effort goes into the scheduler to make sure that the resources are being allocated fairly and appropriately. If you start exceeding those resources, it'll kind of kill jobs. So in general, you shouldn't be able to break something, and if you can, it suggests that there's a problem with the way the system was set up or orchestrated.
Yeah, totally. And a lot of work does go on behind the scenes, like you said, to make sure that the resources are shared fairly, and totally agree. If something's going wrong, chances are we'll notice, and that we know that people aren't HPC experts. Researchers are not necessarily, they're not meant to be HPC experts. I think Inga, when we had kind of chatted a little bit beforehand, and I'm giving things away, but she said HPC is a tool for researchers. So it's not expected that you know how to use it perfectly when you first get started. So yes, I think that's a really good point, Joe. And I did notice that there was a question from Yvette in the chat, and we'll go to that one now. And this will be open to all the panelists if anyone wants to jump in. But she wrote down, looking back, what would have helped you the most when you were starting out? We covered a little bit of it before, but is there something specific that would have helped you? But something you wish you knew when you first started out?
I think just basic scripting would have helped hugely, just from going from, just pressing buttons on your favorite program to actually writing a command that is correct in syntax, correct in many different ways. As a biologist, that was a very steep learning curve. And how to install software on Linux system. It's also not intuitive at all, at least at first. Eventually you get the hang of it, but was not an easy thing. So some basic, I guess, computer science should be mandatory for biologists in this day and age.
I wish NeSI existed when I got started, to be honest. And the reason I say that is that there wasn't really anybody to ask or get help from. I mean, we were in a research group, and as a bachelor's honours students, you kind of just asked the senior PhD students, who were the ones that were looking after things, how to do various activities. But I want to say there's almost like that kind of godlike scenario that they're super smart PhDs, and you don't want to worry them, and you don't want to kind of bother them. So you feel you're not that confident to ask questions. And I wish advice to a younger me would have been to be braver and ask more questions. Because most of the time people are just thrilled to explain things to you. It makes them feel chuffed that they're kind of smarter and they know how to explain things. And yeah, so I wish I was a little bit more confident asking questions earlier on.
Really interesting. Yeah, that seems to come up a lot. The comfort in asking questions is always really helpful. But I wonder how to, if only we could, get into our minds when we were a little bit younger and be like, no, other people have the same questions, It's just that encouragement to ask questions. So I will just reiterate that if you do have questions, flick them to NeSI. We expect them, we are looking for them, and we are always happy to answer them. And so next question I kind of wanted to direct to all of you guys. When I asked this to you before, you all had a very similar answer, and it was, how often do you get stuck? And this was a question about when you first got started with HPC, but I think it's probably the same answer now. But how often do you get stuck when you are using these high performance computing resources, and kind of what do you do? Anyone want to take that one away?
Well, Denny's in the audience, so I really can't lie. All of the time, I still get stuck all of the time. And part of the reason is we're constantly trying new ways to analyze our data, to build our genomes. And the field is just really fast evolving. Like every day there are new programs, new slightly better ways of doing things, and you want to try them all. So, and Denny has forged through all of this with us through the consultancy, which has been fantastic to have. But yeah, still get stuck all the time.
Any comment, Denny? I think you're muted if you're talking.
Sorry. Well, it's my nightmare to deal with bioinformatics software stacks. It's probably at a stage where computational physics or chemistry was maybe 20 years ago. The software is still evolving at a rapid scale, and nothing is stable enough, and we still can't pick what's good. to do all kinds of things. So we'll get there. And yeah, I mean, the other thing is that their compatibility with the HPC environment is, in all environments in general, is still not at that optimum level either. We take a look at some of the customized code for physics or chemistry. They're just fantastic. They work very well in a parallelized environment, but bioinformatics, no, still getting there. So happy to assist, but I think I give minimum help, and it's a lot of researchers doing most of the work, and they're great. They're just figuring things out themselves, and I constantly learn from it as well. So yeah, it's brilliant.
Thanks, Denny. And I think that there is a question now in the chat. And this can be directed to all our panelists again. What resources do you use when you're learning things about HPC now and in the past? So are there any resources you would recommend for people?
My probably go-to is just Google, if I'm completely honest. The sort of general field of HPC's got quite broad now, and you're seeing more and more people logging things on Stack Overflow or various websites that actually a lot of the time the hits you're looking for can be found just with a simple Google search. So I don't tend to go to direct resources unless it's something like a particular software stack that I might be trying to find on NeSI. And I will say that NeSI's pages are really well indexed by Google. So typically just putting, whatever your search query is and NeSI in your search line will pull up something from their support pages, which sort of saves necessarily trawling through their resources specifically.
Other resources? Inga, yeah.
Yes, so people. So yeah, we haven't actually run anything on NeSI directly really since Pan was turned off. So we were running CSM on Pan. And then Maui wasn't ready for our next project, which was running the New Zealand Earth System model. So Shona Mackie, who's just left and moved to Norway, actually ran all of her runs on Monsoon, which is the UK HPC, which had enormous challenges of its own, particularly getting the data back. But yeah, so we were, because I'm not an expert in this, we were hiring in people who actually were experts in this. So Shona, who's just left, and now we've hired Max Thomas, who's currently at the University of East Anglia, because there is really no sea ice climate modelling expertise in New Zealand. I certainly don't regard myself as an expert. So we're hiring people with much higher level skills than I've got and the rest of the team got to try and build up that capacity in New Zealand. Obviously with the border closure, that's a challenge at the moment. So the initial plan is that Max will be starting remotely and trying to use Maui from the UK. So kind of the reverse of what Shona was trying to do. But yeah, but that's an issue we're working through. But yeah, it's certainly, there is a lot that you can learn, and you can learn quite quickly. But some of these things you need 5 years of training to be able to really operate at that level as well. So my assumption is I'm not going to be able to do everything, and we need to, apply for the grants and bring the people in who've got that expertise, who can then build up the capacity for students and others in the group. Yeah, so Cecilia really helped us getting started with CSM, and so that's quite a different model from the New Zealand Earth System model. So currently we're analysing some of the CSM data, but we're also running the New Zealand Earth System model. But both of them do generate very large amounts of data. So that was a challenge for me when I was first coming to grips with it, how much data model output we were generating and how we were going to move it around the country.
Really neat. Okay, interesting. Yeah, and that's a really good point. People that have the really advanced HPC skills, they have built that capability over long periods of time. So people are often, those resources, and reaching out is a really good way to get help. Any other resources you would recommend from our other panelists? We'll go to another question. So we had a question from Laura. How often do you use HPC these days, and how long are your jobs normally running for? I know that can vary quite a lot depending on what you're doing, but it'd be interesting to see from each of you guys what your jobs kind of normally look like. So how often do you use HPC, and then how long are your jobs? Andrew, why don't you take that one?
Yeah, so my PhD work is using HPC pretty much all the time. The depending on the configuration of the model I'm using, jobs take anywhere from 2 days to 3 weeks, running on several hundred to around 1,000 CPUs, like cores at a time. And yeah, I do all of my data analysis on, so Cheyenne in the US has a cluster built attached to it, which is for data analysis rather than compute. So I'm doing most of my analysis on there as well. So pretty much every day I'm on there in some capacity.
Great. And I remember you saying when you first were getting started doing these jobs that lasted, 2 days or something, and you had maybe a minor mistake in them and they would fail. What was that like as someone getting started, and how did you get through that kind of learning curve?
It was tough as someone on like a roughly 6-month honors project when you find out your simulation was wrong twice and it takes 2 weeks to rerun it. But it was a good learning experience, and fortunately there weren't too many consequences because at the time we had basically unlimited compute time. I'm a lot more careful nowadays because there's so many more users on the systems here. There's very strict allocations on how much you can use. So if I mess something up, it can be expensive. So it was a good learning experience to have that freedom early on.
Neat. Someone else want to say how often they use HPC and what their jobs look like? Manpreet.
Maybe talk about this. Across the year, I go through phases because I do a lot of field work and I do a lot of lab work, and then we have sequencing, which takes time. So it can be nothing for months, and then suddenly I will try to take over all of the GA nodes or try to submit a lot of jobs. Good jobs will take between 2 days to a week. Horrible jobs will take, I think the one that's currently still running is now 2.5 months going, and we're pretty sure it's not working, but we're afraid to pull the plug because it's been going for so long. We want to get something out of it. As you can see, Denny is grinning because, yeah, we've gone back and forth over this job, and we should just kill it, Denny.
But that's good to share, because then now we all know sometimes running jobs is a little bit of a gamble. It's a little bit of an experiment, and yeah, so you never know what's really going to happen. Inga or Joe, want to share your HPC jobs?
Yes, so at the moment we're not using NeSI at all, apart from we've got a small allocation to maintain access, and that's because we haven't written up the previous model output yet, and we haven't got Max started yet on Maui. So, but when Andrew was running it, I think the main jobs you were running, Andrew, would run for about a week and generate 700 gigabytes of data in the process, and it's a highly parallelized code. So. And initially I was quite worried about that. I was like, we're landing on 10% of the cluster and occupying it for a week. Is that a problem? And as Andrew said at the time, that wasn't a problem. There was enough capacity in the system. The New Zealand Earth system model is bigger again. So it's generating quite a bit more data. But at the moment, as I said, we're running on the UK supercomputer. So that's been an ongoing discussion with NeSI when I say, when we land on Maui, this is how much we're going to use. And they're like, okay, we're not going to ring fence that for you just yet, because when you do, that might start causing problems for other people. So we have been kind of holding back on that. And that's why it was great to have that access from the UK Met Office to their computer to be able to use in the interim while everything was getting set up. So yes, so we're very spiky, I guess. We don't use it for a long time and then suddenly we're using a lot and then we go away and write it up. But yeah, that's just the nature of the way climate models really operate.
Yeah, so I mean, all my students are a mixture of pure theory students or sort of experimental in theory. So most of the time someone's running simulations, I guess. Personally, I don't get on the tools or on the keyboard nearly as often as I'd like to, and just with some extra administrative responsibilities, etc. In terms of length of job, typical stuff now is probably, a small number of weeks to a small number of months. My longest ever calculation was 14 months, which was kind of coarse grain restartable every 6 weeks-ish. So that was quite a long journey, and that was as paralysed as it could be in that era. The worst thing though, I think, thinking of Andrew's experience with having jobs sort of crashing and having to rerun them, as a part of my PhD, I had a particular benchmark calculation I wanted to do that was going to run, or evidently took about 120 days to run. But we restarted that thing so many times, we just seemed to have the worst luck with power outages and network drops and all sorts of things. And the last time I did it, I actually ran it concurrently in 4 different locations on 4 different supercomputers around the world. And of course, Murphy's luck would have it that not one of those 4 was interrupted. And so I ended up with 4 copies of the same job. But you start getting a bit desperate when you really need a number for your PhD.
Interesting. Wow. Thanks for sharing that. We have another question from Yvette, and since Joe, and I didn't mention this before, but you do a course at University of Waikato for students looking to develop their HPC skills. Would you like to just give a little bit of, give us a little summary of what that course is and what you do there at University of Waikato?
Yeah, sure. So, so what we've sort of, I guess, identified is that, like Manpreet said, you know, you often come through a science program like biological sciences or chemistry or something like that, and you don't actually learn any computer science or data skills or anything that would be relevant to then go into the research space. So we created a paper for postgraduate students, intention is non-computer science students who can kind of get tooled up with an intro to the Linux command line, a bit about how a supercomputer operates and the scheduler and how that kind of works. A little bit about scaling and parallelization, so people can know, you know, it's not just increasing your core count. Sometimes that doesn't make the job run faster. You know, different parallelization schemes, that sort of thing. And then lastly, we get this, a little bit around some scripting and automation to make sure you're not doing the same manual task 100 times, but learning to write a simple for loop or something like that to automate. And then we get students to work on a little mini research project to kind of put those skills they've learnt into practice. And I think an important part of that is also learning how to write up results that have been generated from a kind of theory basis. A lot of the time with sort of computational work, you generate massive amounts of data. And I don't just mean in a per gigabyte kind of sense, but there's a lot of information that you could put forward. And it's about creating that narrative to explain what the data is telling you. And you know, the simple skill of learning, well, what goes in the paper versus what goes in the supporting information or the supplementary or whatever it's called in your favorite journal. So that's been kind of a paper. We've done this, it's our 2nd year now, and yeah, a massive kudos to NeSI and the team. We couldn't have done it without them. It's been really, really great having that support base to work with for that. And interestingly, this year we do have 2 computer science students actually in the paper. So they've done full comp sci degrees, and they're actually still learning stuff in our paper that they wouldn't have learned in their normal comp sci degree. Because, you know, how to use a national scale research facility isn't something that's generally taught. And, you know, even how schedulers operate and efficient, you know, use of compute resource. So the key metric being throughput, you know, when can you answer your science question, not how fast can you make one individual calculation go. And that's, I guess it's a general project management skill that we're trying to teach them.
That's so cool. And yeah, I imagine that's very, very helpful sort of paper to have access to. Like you said, it's hard to find a paper where you can get taught those sorts of skills. And I asked you to explain that a little bit because I reckon that sort of context might explain why I'm directing this question to you initially. But have you used Jupyter Notebooks, and do you see this as playing a role in making a difference in the use of HPC at all in the future? And also the potential ability to share code and tools easily. So I figure you might have a little bit of an interesting perspective on that question.
I probably should, but embarrassingly, I haven't actually any experience with Jupyter Notebooks. I mean, I vaguely know what they are. It's kind of on my to-do list of things to learn and to get a little bit better in that space. But yeah, sorry, I can't actually help you with that much. I do know we're talking about a new course for next year, actually way back at 1st year level, where we're talking about trying to use Jupyter Notebooks to help students not so much write a notebook, but to be able to have an easy input framework to do simple modeling. So, you know, I do think it has a wide range of applications, but not something I've got a lot of experience with.
Do any of our panelists have any thing to add to the Jupyter question, or else maybe a NeSI person that's in the room? Oh, Andrew, why don't you go ahead?
Yeah, so I've used Jupyter a lot, almost every day at the moment, because I'm working remotely. It's really convenient. So I'm using Jupyter notebooks running on the analysis cluster on the supercomputer here to analyze all my output. And so for those not familiar with them, they're a tool where you can run your analysis in a web browser, and it kind of breaks up your code into cells. And you can also add like nicely formatted descriptions of what's happening. And it has the, you know, if you're generating plots, it has the code and then the plot immediately afterwards, and it's all presented really nicely. And there's some idea of using this to either supplement or just replace the typical scientific paper, especially in domains where this kind of analysis is common, because it lets people actually see what you did and reproduce it. So there's a little bit of a push to do that here in the US. There are some climate and atmospheric science papers where I've seen them reference a Jupyter notebook that they've published online, and you can go and see their code and how they analyze their output. But also for me, running it on the analysis cluster on Cheyenne, I have access from the Jupyter notebook to all of the, I can, you know, if I'm analyzing a particularly big data set, I can access up to 1 terabyte or more of RAM and multiple CPUs if I need to do some computation that's intensive without all the overhead of like trying to get it to run on the supercomputer itself. I can kind of do that interactively, which is really nice. So I'm a big advocate for Jupyter. I think it's great.
Awesome. Thanks for that. And I think that we have one of our NeSI staff that's going to put a link in the chat. NeSI is working on providing Jupyter for NeSI users in the future. We have kind of an initial start going on for a couple people that are testing Jupyter notebooks. And so Chris is going to give you a link so that if you want to check that out, you can have a look at what it looks like, Jupyter at NeSI. Okay. And I'm just having a look at the chat if there's any more questions. Oh, we do have one. And so what are the biggest changes in your field, your research community, when it comes to using HPC? So does that, Alexandra, do you mean, so how has it kind of changed over time? HPC usage? Yes, so how has HPC usage changed over time in your field or community? Anyone want to dive into that one?
Well, it's been absolutely transformational. A few years ago, you couldn't even assembling a genome was something big consortiums used to do because there was no easy access to HPC resources. There wasn't even understanding across biology as much as it is now that you can just submit big jobs and assemble complex large genomes. And that's actually gone hand in hand with the development of sequencing technology, which is much cheaper now. So it's individuals can assemble small genomes easily, which was something that was unheard of before. Another thing, and as Denny and I were talking earlier about it, that the code is always evolving, the program's always evolving, and so we've had to step up our game in terms of learning new things all the time, and I think that's been one of the biggest changes in the field. And it is generally now expected that if you're doing anything with cellular processes, if you're doing anything with phylogenetics or genomics or evolution, you come with a background of understanding at least how high performance computing works, even if you haven't tried it, but expecting to learn it, pretty much.
Very neat, cool. Anyone else want to jump in with how HPC has changed their field?
Yeah, so I guess for climate modeling, like I say, like I'm not a climate modeler, I'm more of an observationalist, and we've come into this reasonably late. But originally, most climate modelers were climate model developers, which is essentially what Andrew was doing in his PhD, but that's actually quite rare. So most people that are climate modelers in the world are really analysing the output from some of the big modelling centres. They're not necessarily improving the model or developing new parts of the model. And that's been the unique opportunity we've had working with Cecilia and then Jeff Ridley in the UK, is that we are actually trying to improve these models and actually hands-on with the actual code and then running them, whereas most people aren't. And again, that's a different kind of HPC. That's downloading output from the big models and then analysing them. But the actual model development stuff, which is originally what most people were involved in, there's now very few, but we're very lucky that with the NeSI capabilities, we can actually make contributions to that internationally. Andrew, did you have anything to add to that?
So I think now being part of a sort of larger modeling community here in the US, traditionally the kind of climate model world is one of the more established high performance computing fields, because it's always taken a lot of compute to run these models. Even 30 years ago, they were running on clusters that were fairly advanced for the time. But now with the advent of cloud computing, there is a push, or there's talk of adapting these models to be able to run on like these giant web servers like Amazon or Google or Microsoft hosts, because the hardware is already there. You just need to pay for the time. And I guess what makes people nervous about that is losing the support of the organizations like NeSI or NCAR in the US. That's as important, I think, as just having the hardware, as having the support to be able to run these things. So it's interesting, the idea of doing this on cloud computing services, but it would have to be managed pretty carefully, I think.
Great. Thanks for that, Andrew. I'm sorry, I can't remember. Was someone else going to add something to that question, or?
I was just going to say that I think, at least in the computational chemistry world, it's become mainstream, I guess. Whereas you might have just had an experimental paper. Now most papers have both an experimental component and some sort of theory element to augment the either interpretation of the data or some sort of prediction, and that's why it guided people down a certain synthetic pathway or that sort of thing. So and that's been about making the tools easier to use, and a lot of the time that's on large HPC platforms.
Thanks for that. And I wanted to kind of continue on this same topic for a little while, but then ask kind of you guys individually how working in HPC has changed your own research trajectory. I think for each of you, you had some really interesting comments on how you've gone into different ways of thinking about your fields because of going down the path of high performance computing. So would someone like to explain how their own personal research trajectory has changed because of this skill development?
I can start.
Yeah, start off with.
So when I first came about assembling genomes, I was thinking about tiny genomes, and I thought that was amazing to be able to do. Today, Denny and I and several others involved in the project are putting together one of the largest, most complex genomes in New Zealand, and I think that shows that the sheer scale of the kind of data science we can do today has been amazing, and that's completely changed the trajectory of my own research. Going from very humble background of assembling tiny microbial genomes to large eukaryotes today. And another thing that it's completely shifted focus for my research has been on the kind of complex questions we can ask this data. So it's not only just assembling the genomes, but we can do hundreds of simultaneous analyses on these genomes and try and understand a bit more about what the genomes mean, what the differences across species, what the differences across populations mean. And that, again, the technology has pushed us to a really, really extreme end of the spectrum of what we were able to do only a few years ago. So it's been really, really revolutionary what you being able to access high performance computing has done for the field and for individual researchers like myself.
Great. Someone else?
Yeah, so I guess, like I said, my PhD was originally on sea ice observations and processes. And whereas now about half of my externally funded grants are very specifically about climate modelling. So it really has sort of changed that scope completely. And again, like I said, I'm not the expert in this. So it's really, I'm the interface and the kind of manager of these bigger groups and hiring in the experts. So both Shona Mackie and Max Thomas in terms of that very specialised sort of sea ice climate modelling expertise. And then Kat Lilly also, who's been helping with the CSM work, has originally got a PhD in geology, but she did a postgraduate certificate, no, a grad, I think it's called, in computer science. So she's actually got all of those kind of computing skills as well as that geosciences background. So just that ability to work with people with those very specialist high performance computing or computer science skills to try and answer these big sort of global scale questions. And you know, when Andrew was running these models, because you're modeling the whole globe, even if we're only really interested in Antarctic sea ice, you suddenly see these weird effects happening, you know, in the northern hemisphere from fresh water melting in the southern hemisphere, for example. So it sort of really expands your scale from what my PhD was, which was very specific freshwater influences on this bit of sea ice and the sort of crystal structure, to now what are these global climate effects long term and even in the northern hemisphere. So yeah, so it's completely changed the sort of geophysical scale of my work, as well as the way that I operate.
Really neat. And anything to add, Andrew, to that one?
Yeah, it's kind of completely changed my research and life. So I, you know, traditionally that wasn't climate modeling wasn't a research direction you could follow in New Zealand very easily as a student, and certainly not in the physics department I was in. But I kind of got lucky to work with Inga and Cecilia during my time there, and now I'm in the US doing that as my PhD. And yeah, I'm really happy it happened. I think before I came across this work, I was considering other like more theoretical directions in physics, and just sort of opened my eyes to being able to use these physics and learning the computational skills to answer more directly real world applicable questions. So it's really changed my whole research direction.
Awesome. Okay, we have one more question in the chat. I think that might be our final question to cover, and then I'll do a little bit of a wrap up, and we'll probably end maybe a little bit before the hour. But so from Jan, how do you check your results and debug your code on the HPC? Do you have a test pipeline, or do you run your code interactively with debuggers on the HPC?
So I'll kick that off. So I guess with the computational chemistry packages we use, there are a standard set of tests that you run to make sure that everything's compiled properly and giving the results you should. So that's kind of one side, is the code working as it's meant to. The other side, though, when you're kind of just running a range of different jobs, is looking for consistency in results or expected trends. I'm always surprised. Sometimes students will turn up and sit down and have a conversation with me, and they'll give me a table of numbers, and you can look at it for all of about 15 seconds and say, oh, that number's wrong. And they'll swear black and blue, no, that's definitely right. And you say, no, it can't be, that can't be, it doesn't follow the trend that's going on. The student goes away, comes back, and 9 times out of 10 sheepishly admits that they've copy pasted it wrong, or they reran the wrong job over the top of it, or something like that. So I definitely encourage people to be discerning when they're looking at their results. It's probably the biggest danger with computational work, is it'll always give you a number. You've got to use your skill as a researcher to know whether that number actually means something. Unfortunately, it's just something that you kind of develop with time and experience, and basically burning your own hands and making mistakes. And you realize to look out for things later on, like, 2 numbers that are identical in a table to 8 significant figures. They're probably not meant to be identical to 8 significant figures. Go back and check that you haven't, made a copy paste error.
Really good one. Anyone else want to add to that? How do you do your debugging? We'll have one more person. Okay, Manpreet, thanks.
a lot of trial and error, and there is the option to run short test pilot jobs on NeSI. So often I use, when I'm starting a new program or using a new set of command line things that I haven't used before, then I try a short thing to see whether the job submits correctly, whether the first few steps of the program run fine. So that's in the troubleshooting your new program end of things. Doing sensitivity analysis. So for some of the statistical models that we run, you do sensitivity analysis to see whether you're getting biologically meaningful results. And again, as Joe was saying, yeah, that is something you develop over time by trying and seeing what works and what doesn't, and two identical numbers are usually a bad sign.
And I think, Andrew, you had a hand. You can add your 2 cents too.
Yeah, so it kind of depends on what I'm doing. If I'm doing more development type stuff where I'm actually changing source code, then there are kind of compiler flags and things I can use to run short jobs and see whether it runs at all. And if not, then it spits out a lot more information. And if I'm debugging more the kind of science that I'm trying to do, like, does this make sense? Then there are, it's a very well-established model that I'm using. So there are kind of standard baselines that are made available for people to compare against. So there are kind of 2 different types of debugging that I'm often doing.
Awesome. Thanks for that. And I think that was our last question in the chat. I would like to keep us on time and even end a little bit before the hour to give everyone a chance to run to their next Zoom meetings or whatever you're doing. So I will just flick up a few ending slides, and then I'll set you guys on your way. So let me share my screen real quick and find where my notes are. They always get lost. Here we go. Okay. So before we sign off, I did want to highlight a service that NeSI provides that some of you may be interested in. So high performance computing, as we've kind of discussed today, is a tool, and it's a tool that most researchers are not going to be experts at using necessarily, nor should they be. You have enough on your plate already, and it's why NeSI has a team of research software engineers who can help you get through problems. So for researchers at most universities and CRIs, this service is provided at no cost to you, but you do have to reach out to NeSI and tell us a bit about your project, what you're looking to achieve, so that we can ensure a consultancy collaboration actually makes sense. So this is just a little prompt for you guys to contact support@nesi.org.nz if that is something that looks like that might be helpful to you. Flick us an email. We really would love to be in touch. And otherwise, that is all we have for today. Thank you guys so much for coming. Thanks especially to our panelists. And that's the end of our panel. If you would like to stay on the call and perhaps chat about what consultancy looks like with someone from NeSI, I think we can arrange that. Otherwise, I'll send you on your way. Thank you so much for coming, and have a good afternoon, everyone.